Hey guys, I hope you guys are doing well and staying safe. In this video, I'm pretty much just going to be talking about pre-lab 5, and if you haven't already done so, can you please go on Blackboard, watch the video for ammonium nitrate and calcium chloride, as well as look at those graphs that I put in there, and then read the lab manual from page 67 to page 71. And then when you're ready for that, then go to page 73, so that way we can talk about this and you guys are all on the same page and it makes a little more sense what I'm talking about. So for this pre-lab, we're gonna be talking about thermochemistry, and thermochemistry is basically the branch of chemistry that deals with heat being absorbed or evolved during a chemical reaction or physical transformations. And for this class, the main things that we're gonna be talking about in thermochemistry are gonna be heat, temperature, and enthalpy. There are other things like specific heat, like heat capacity and other things, but for this class, just heat, temperature, and enthalpy that we're going to be talking about today. So with that being said, I want to make sure that we understand these terms because they're not the same. Heat is not the same as temperature, and it's not the same as enthalpy. Heat is just a transfer of energy from a higher temperature to a lower temperature, or from something being warm to something being cold. So it's like a phenomena type of thing. Whereas temperature is just the average kinetic energy or the average motion of molecules in the system. So how well they're moving together and stuff. And enthalpy just gives you information about the heat content and the capacity to do non-mechanical work for a system. So in most cases, scientists like to use enthalpy as it gives a better description of how a system can interact. So then again, heat is just a phenomenon. Temperature is the average molecular motion of molecules in a system. And enthalpy is overall the heat content with the capacity to do non-mechanical work. So if you guys turn to page 73, you see that the question for pre-lab is, what is the heat of solution? So we're gonna make salt solutions. We're gonna have a salt, we're gonna put it in water, and we're gonna determine what's gonna be the enthalpy of that. So as we know, when we put salt in water, it's gonna dissolve, correct? So, one little thing I wanted to say too was that enthalpy, pretty much I look at it as being the relationship between the system and the environment. It gives a better description of that. But yeah, so with the calcium chloride and ammonium nitrate, we're gonna try to determine the enthalpy of those salts. Right here I have an example, so I'm gonna work it out. But first I want to talk conceptually about it before I start working stuff out on the board. But so I have anhydrous sodium acetate, right? And I'm gonna put it in water. So before I talk a little bit more about it, I want to talk a little bit about water. So water is H2O, and oxygen is really electronegative. And when something's electronegative, it means that it wants to pull electrons from its surroundings. And so what is happening then with water is that oxygen is pulling electrons, like electron density, from the hydrogens. And the hydrogens are kind of weak, so they can't hold too well their electrons, so they'll let go a little bit. So when this happens, we know that water is a neutral molecule, right? But it creates partial charges, meaning that hydrogen can become partially positive and oxygen partially negative. If oxygen is taking more electrons than what it can hold, then it becomes partially negative because electrons are negative. And if electrons are being pulled from hydrogen, that means that it has less electrons than protons, so it becomes partially positive. So with that being said, when a salt goes in water, those water molecules are going to break that salt between the positive and the negative part. So we know the sodium acetate, sodium is positive, it's in the first group of the periodic table, so it has a plus sign. And then this C2H3O2 is an acetate group, and it's a -1 charge. So when it's dissolved in water, the molecule breaks apart, right? And so what's happening is you're gonna have oxygens facing the sodium, because positive and negative attract each other. So the oxygen is going to be close to the Na, and this little G sign, it just means partial in math. So I'm just saying partially positive, partially negative, partially negative, partially positive. I'm not giving it full charge, I'm just giving it a partial charge. So this acetate group here, the oxygen, the hydrogens are gonna be the ones that are gonna be close to it, because the acetate group is negative, and the hydrogens are partially positive, and opposite signs attract. So what's happening here is that the salt is being dissolved, right? So if I were to do this in a cup of water in front of me, that cup of water will start to get warm. And the reason for that is because more interactions are being made than broken. So it's warming up. And when the solution starts to warm up, that means that it's releasing heat, right? So when something's releasing heat, that means that the enthalpy is negative, because it's releasing heat from the system to the surroundings, right? So the sign of my delta H would be negative because it's becoming warm. It's releasing heat. And when that happens, so the temperature of the surrounding is warm. And when that happens, that's called an exothermic reaction. And exothermic just means that it's releasing heat, and that's why it's becoming warm. But if more bonds were made than if more bonds were breaking than being made, then that means that it's taking more energy from the surrounding to the system to make bonds. Because if you to break bonds, if you want to break a stick, so I want to break this, it requires energy. I have to go like this, right? So if I want to make bonds or interactions, I need energy from the surroundings. So if more bonds or more interactions were being made, then that means that it's taking more energy from the surroundings for that to happen. And that way the system would be endothermic, meaning that it's becoming colder in the surroundings and it's taking heat from the surroundings to the system. And again, just so that you guys know the difference between exothermic and endothermic. But to say it one more time, exothermic just means that there are more interactions being made than broken. Because to break a bond or interaction, you need energy. Just like breaking a stick, you need energy for that. So it's more bonds, more interactions are being made. So it's releasing more heat than what it's taking. Sorry, it's releasing more heat than what it's taking. So that's why the surroundings become warm. And when I talk about energy here, I'm mostly talking about heat being released. So with that being said, I wanna talk about the calibration of the temperature probe. So if you guys watched that calibration video, then you guys can understand this a little bit. So in order to do this whole experiment, we basically wanna see the temperature change when you add salt to the water. So for that, there's something called calorimetry, and it's on page 68. You have a coffee cup calorimeter, and basically it's two styrofoam coffee cups inside each other, and it's gonna create a closed system, meaning that no matter can go into it, but heat might be transferred. If it was an insulated system, that means that no heat is being interchanged between the environment and the system. Everything's is contained. But this, it's not a perfect insulator, so we can call it a closed system. If it was an open system, pretty simple, it means that matter can go to it. It means that it doesn't have a lid on it, and heat can go in and out, and matter can go in and out. So in this case, we have a closed system, and we have two styrofoam cups right here. There's a steering plate right here. There's gonna be a steering rod in it, and there's gonna be a temperature probe, which is right here. Sorry, I meant to say stir bar, not steering probe. So a stir bar is gonna be in it to mix the solution, right? It's that little dot in there, or that little circle. And then that little stick in there, that's a temperature probe. That basically measures the temperature that's changing in your system, right? So we wanna measure this temperature so that we can determine the enthalpy of our solution. So first we gotta tell the probe what is cold, what is hot, and what is room temperature. So we have 3 beakers right here. You put 1 beaker with ice water, the second beaker with room temperature water, and then the third beaker with boiling water. Then you tell the program, you stick the probe in it, mix it up a little bit, and once you see the voltage on the computer that's not changing anymore, it's not fluctuating, it's constant, then you give it a number. And it's gonna tell you, okay, well, I pretty much know what this is, but can you tell me, is it cold, is it hot? And that's, you put on the computer 0.0, meaning that that's ice, that's cold. And the program's gonna be like, okay, got it, what next? So next one, you put it in room temperature water, wait until the voltage stops changing, and basically the program is telling you, all right, I'm ready, tell me what this is. Then you tell it it's room temperature water, you put 24, 22.0, whatever room temperature you have in your lab or whatever. And in my case, it would be 24.0 degrees Celsius. And then for the third one, you have a beaker with boiling water. You put the probe in it, wait until the voltage stops changing, and you tell it what it is, 100.0 degrees Celsius, because water is boiling. Once you have that temperature probe ready, that means that you can determine your temperature change precisely, because it's being the temperature probe was calibrated. So with that being said, I want to go to page 73, where we have a pre-lab, and right there, if you guys looked at the graphs, you should have your initial final temperature from the graphs, but I'm going to talk a little bit about it in here. So let's say I have my ammonium acetate, I want to do the experiment. So I grab the bottle, I weigh out 1 gram, in my case it was 1.012 grams. I look up on Google what's the molar mass, because later I'm gonna have to find the moles of my sodium acetate. So to find moles, you divide the mass by the molar mass to cancel out those grams and end up with moles. So I'm gonna need to find moles later, so that's why I looked up my molar mass of sodium acetate. And if you guys have to do that, you can find you can type on Google molar mass of calcium chloride, and it'll give it to you, and that way you can use it to do your mole calculation. So then I got a graduate cylinder, and I measured out 60.0 milliliters of water, and in that cup, in that coffee cup design right here, I put 60 milliliters of water in there, right? And then let the stir bar stir and mix my solution. Well, mix my water, because I haven't added anything to it. My grams of sodium acetate I have it apart. I don't have it in the cup yet. I'm gonna add it, but not now. So I just have water in there. I have the 60.0 milliliters of water in there, right? So I set up the program and I start recording data. So this right here is what my data look like. Right here. Okay, so the x-axis in this time is time, and it's in minutes, and it took about 5 minutes. And on the y-axis is the temperature, and it goes from 24, 25, 26, 27 degrees Celsius, just to put it to scale. So when I start recording just with the 60 milliliters of water, I haven't added the sodium acetate yet, my graph pretty much stays constant. Because right now in this graph, we're looking how temperature is changing over time. So I just have a cup of water there, 60 milliliters of water in that cup, and I have the probe in it, and just like right here. And nothing's pretty much changing, it's mixing, the water's mixing, but the temperature's not really changing. So it's a flat line, right? But about close to minute 1, I take my grams of sodium acetate and I open the lid, put it in that cup, and close it really quick, right? So now I have my sodium acetate in that cup as it's stirring with the stir bar. So the temperature probe now is reading the temperature change when I add my salt to the water. So when that happens, it starts getting warmer and the temperature starts rising, right? It reaches a point and then it starts going back to equilibrium or to room temperature. So that's what my graph looked like for this. And basically it's telling me that it became warmer, right? So, like I said, it became exothermic. It was exothermic because it's releasing heat. And if you release energy or heat, then the surroundings are becoming warm. So, when you guys look at the graph, on the left side, you guys are gonna see a range of temperature values on a table. Right there, you can take your initial temperature, which is the first one, and the final temperature, which is the last one. If you were to have that table, you had to extrapolate the graph. And to do that, super simple. You just draw a slope on the two parts of the graph. So a slope on this incline, and then a slope on the second incline. Right there. And I see where they meet. Where they meet somewhere right here. Then I trace it back to the temperature axis. And I measure with a ruler, and it tells me it's 26.2 degrees Celsius as my final temperature. You guys probably won't have to do this because, again, on your graphs that I put on Blackboard, you guys have your initial temperature and your final temperature on the table. So there's no need to extrapolate the graph. So with that being said, I collected my data. So with all of this, I can fill out these parts of the pre-lab. I know what my initial temperature is. It's right here, 24.0. I know what my final temperature is. It's 26.2. I know what my water volume is because I told you it was 60.0 milliliters of water that I put in that cup. I know my grams of salt because the balance, I measured this out in the balance, and it was 1.012 grams of sodium acetate. Then the rest pretty much is just gonna be calculations. So the data that we collected here was mass of the salt, the volume of water, and the temperature, the initial and final temperature of that solution. Again, this is a solution where we have a solute and a solvent. Our solute in this case is the salt, and the solvent is water. So now I'm gonna go with the data analysis, and I'm gonna do my data analysis so you guys can see, and hopefully you'll be able to do the pre-lab 5 with this. So I'm gonna move this real quick. There we go. Okay. So, with this in here, I put up my data on the board, and so like I said, we have some data we just collect. We don't do any calculations to, but here we have to do some calculations to get the delta H or the enthalpy of our solution. Another thing is when you guys do these calculations, you have to write the delta, that little triangle sign, in front of the H always. You will never see H by itself because H is enthalpy is a parameter that basically depends on the initial and final state. So it's not like a value that's specific for something. You will never see it without the delta H state function. It basically depends on the initial and the final state. It don't matter how you got there. So it's like if I were to go from SciTech, from our room, from what's it called, the 4th floor to, let's say, Colchio, right? It don't matter if I took a plane from SciTech from the 4th floor to Colchio, or if I start running really fast, or if somehow I went underground to go to Colchio. Like delta H don't care about how you got there, it just cares that you went from one point to another point. So that's why we always have to put the delta H in front of it, because otherwise without the delta it will be meaningless. So in your calculations, make sure you guys write the delta in front of the H. Temperature, normally temperature, delta just means change. It just means final minus initial. So as I just said, enthalpy always has a delta in front of it. Temperature doesn't always have to have a delta in front of it, but when we're trying to get the change in temperature, then we put a delta in front of it, meaning that we want to know what the final and the initial temperature was, what the difference between those was. So delta T is T final minus T initial, and I got that from my graph. My T final was 26.2, my T initial was 24.0, meaning that it went from room temperature, 24.0 degrees Celsius, it warmed up to 26.2 degrees Celsius. So that difference is 2.2. Then the next thing I want to calculate is my Q of water, which is the heat of water. And there's a formula that's on your pre-lab and basically says that the mass of water times a constant value, which is CS, is called the specific heat of water. It's a specific heat of water, and it's 4.1 4.184 joules per grams per Celsius. So that's the constant there. And then the temperature change. So we know the delta T right here, we got it there. This CS, or that specific heat, is a constant, it's given to you. And then the mass of water, we gotta get that. We know that we measure out 60 milliliters of water. So we have the volume. So how do we go from volume of water to mass? We're just gonna assume that the density is 1 gram per milliliter. So multiply 60 times 1, and it gives you 60.0 grams of water. So basically the same amount of volume is gonna be the same amount of water. The same mass of water, sorry. So I got 60, so now I can put that in there, and I do my calculation, and I get that my heat of water, or my Q of water, is 69 joules, because the grams and the Celsius cancel out in the calculation. So once I have that, I can actually find my heat of solution, or the Q of solution. Because the salt is dissolving, then you just take the opposite of that heat of water. So your heat of solution is going to be the opposite of the heat of water. In this case, it's just going to be negative 69. Also keep track of sig figs. We know that when you have the temperature difference, when you're subtracting the temperatures, you have 1 decimal place. So when we subtract sig figs, we go by decimal places. So 26.2 minus 24.0 should be 2.2, meaning that it has 1 decimal place, and now I have 2 sig figs. So when I do my calculations, I should have 2 sig figs here and 2 sig figs there. I'm gonna write it here again. 26.2 minus 24.0. I have 1 decimal place, 1 decimal place, right? We go by the lowest number of decimal places. So 2.2. So now I have 2 sig figs. So then my answer should have 2 sig figs, because this mass is 1.012, which is 4 sig figs. This constant value, we don't count it because it's not a measurable value, it's a constant value. And delta T is 2 sig figs, so we have to have our Q of water as 2 sig figs. And the same thing is gonna go with the Q solution. It's two significant figures. It's gonna be negative 69. And then now that we have that, we can find our delta H, which is the enthalpy change. So for that is the Q of solution, which is this one right here, over moles. N means moles. So all we have to do is just calculate the moles. And as I previously mentioned, you have to use the molar mass of your salt to get the moles. So I got my grams of salt divided by the molar mass. It's gonna give you moles of my salt. In this case, I got 0.01234 moles. So once I have that, I can divide this number, the Q of solution, divided by my moles, and it's gonna give me this number. This negative 5,593 joules per mole. Also, joules is a measurement of energy, and we use it a lot. But our question is asking us to put the answer in kilojoules per mole instead of joules per mole. So all we have to do is just take that value, divide by 1,000, and cancel out joules, and we end up with negative 5.6 kilojoules per mole. And remember, we gotta keep track of sig figs again. Q solution was 2 sig figs, so this should be 2 sig figs as well. Number 1, question 1, after you finish out the table, it's asking you to show the work. So make sure you show all your calculations with the sig figs from beginning to end. So I want to see how you got this from temperature. I want to see how you got this delta H from your change in temperature. Then question 2 is asking you to use claim evidence justification to determine whether your salt was exothermic or endothermic. So claim, evidence, and justification. My claim here is that the dissolution of anhydrous sodium acetate in water was exothermic. My evidence is that I can just say that the temperature changed positively, meaning that the final temperature was higher than my initial temperature, meaning that it got warmer. You know, when it was initially was room temperature, and then it went up to go warm. And if it gets warm, you know, like means that heat or energy is being released into the environment. So that means that it's an exothermic reaction. So part of my evidence is saying that the change in temperature is positive, or I can also say, I can also say that the change in enthalpy was negative. And for that reason, that's my evidence. I can say that my reaction was exothermic. For my justification, I can just say that, you know, when this happens, energy is being released to the environment from the system. So the system is releasing the energy in form of heat, making the surroundings warmer. So basically, I'm repeating the same thing over and over again because justification is basically what I had just talked about. You can say that temperature change, and you know that's part of your justification. That's an observation that you can talk about, and say that your enthalpy was negative. You know, if it's negative, that means it's exothermic and it's releasing heat. If it was to be endothermic, then that means that my delta H is positive, and my change in temperature would be negative, meaning that it started at some temperature, at a room temperature, but then the temperature got down, meaning that it got colder, meaning that it took energy, took heat from the environment to the system, and then that would be endothermic. So make sure you guys do this. Email me if you have any questions. I think that's it for the pre-lab, and I'll post a video later about the proposal. But I want you guys to just process this first so we can talk about the proposal. And that's pretty much it for this video. Make sure you guys do the peer review today. And yeah, that's it. Stay safe, wash your hands, and I'll see you.